Hello everyone, this is Aidan for Fluid Mechanics 101, and today I'm going to be talking to you about how do wind turbine rotors really work. So just to give you an overview of what I'm going to talk about today, I'm going to start out by going through how wind turbine blades are constructed. Then I'm going to look at why a wind turbine blade is more complex than aeroplane wings, and we're going to follow up from that with why a wind turbine blade's twisted and what happens to wind turbine operation when the wind speed changes. And as always with this series, we're going to be focusing on the concepts and the ideas rather than the mathematics behind the wind turbines. So just to start things off, there are many different types of wind turbines which you may see out and about, and I've got three typical example designs which you may have seen. And just to highlight here that we're only going to be looking at the horizontal axis three-bladed rotor design. So that's the design on the left, as these are the most common designs. And it turns out that these devices are lifting type devices, and they're actually more efficient than drag type devices, which you see on the right. So this is the type of wind turbine we're going to be focusing on today. So how are wind turbine blades constructed? Well, it turns out that wind turbine blades are actually very similar to wings that you see on aeroplanes. And what I mean by that is that actually the blades are constructed from a set of aerofoils. As you can see from the diagram, if you were able to see through the surface of the wind turbine blade, what you'd see is a set of aerofoils extending all the way along the blade from near the root all the way out to the tip. And that construction is really going to govern the aerodynamic performance of the blade and how the rotor as a whole operates. And that's really what we're going to dive into today. So before we dive into looking at how do wind turbine blades actually work, it's worth just doing a brief recap of the aerodynamics of airfoil sections. And at this stage, I encourage you, if you haven't already, go back and look at a previous video which I've done on this channel for how do aerofoil shapes actually work and how do aerofoils generate lift, because that will really help you understand the rest of the content in this video. But if you've done that already, just to give you a brief reminder of what happens is when we have some free stream wind coming in at a velocity u, as you can see from the diagram, and this wind comes in and approaches the aerofoil chord line at some angle, alpha, and we call this angle the angle of attack. And what happens as the air flows over the top and bottom surfaces of our aerofoil is that we generate a pressure distribution. So the pressure always acts normal to the surface and forms a distinctive shape on the top and bottom surfaces of the aerofoil. And if we integrate that pressure distribution around the aerofoil, what we find is that we get an overall force vector F that represents the net force acting on the aerofoil section, and we can resolve that into lift and drag forces L and D. And at this stage, if this isn't making too much sense, I again recommend that you go back and have a look through that aerofoil introduction video. It'll help. All of this will make a lot more sense. So before we proceed, the main thing we want to flag up is the effect of this angle of attack alpha. So what happens is, generally as the angle of attack increases from 0, what we find is that actually we get an increase in lift and an increase in drag. And what that might imply is that if we want to get a greater force on our lifting section, then we would just continue to increase that angle of attack as much as possible. Now, you may remember from the previous video that actually if we increase the angle of attack too much, then the aerofoil stalls, as you can see from the diagram. And what happens when we stall is we get a sharp drop off in lift and a sharp increase in drag. And this is highly undesirable whether we have an aeroplane or a wind turbine rotor. We really want to avoid stall. And to do this, we need to make sure that the angle of attack alpha isn't too large. So now, going back to our wind turbine rotor, we're going to have a look at the blade. So perhaps the easiest way to understand what's happening with a wind turbine rotor blade is to take a look at the rotor top down. So if we're on top of the wind turbine rotor and we're looking down on the blade as the blade's at top dead center, what we'll see is something like the diagram on the right. And again, we can see that the blade is made from a set of aerofoils from the root all the way up to the tip, and the wind in this diagram is approaching from the bottom of the screen, and that blade is rotating from right to left, as we can see. Now, what we want to do to understand how this blade functions aerodynamically is to just take a slice through that blade somewhere along the span, and we can take halfway just for this explanation. And again, looking top down, what we see is that there's an aerofoil section where we took a slice through that blade. And what we're going to use here is we're going to use a blade element diagram to understand the flow around this aerofoil section. So perhaps the most important thing to note with a wind turbine rotor blade is that the velocity incident on that blade has components from the free stream wind and from the rotation. So that's the diagram on the left. You can see that we have the free stream velocity is approaching from the bottom of the page, and then the velocity due to the rotation of the blade relative to the blade this time is left to right. Now if we contrast that with the velocity experienced by an aeroplane wing, we remember that of course the aeroplane wing doesn't rotate, and we only have that single velocity component from the wind incident on the aeroplane wing. So straight away here we can see that the flow over the aerofoil is slightly more complicated for the wind turbine blade than for the wing, particularly as that rotational velocity component that you see there is actually going to vary along the blade. So the sections near the root are rotating relatively slowly, whereas as we move out along the blade all the way up to the tip, those sections at the tip are rotating a lot faster. So that rotational velocity component is going to be a lot greater, which will change our flow angle. And don't worry if this is seeming a little complicated at the moment, we're going to dive in a bit more detail and explain what happens. So I've got two diagrams for you, and on the left we've got an aerofoil section near the root of the blade, which is rotating relatively slowly, and as you can see from that velocity triangle, the rotational velocity component given by omega r is fairly small, whereas if we look at the diagram on the right, we see that that rotational velocity component, omega r, is much larger, and that's because r, which is the span-wise distance from the hub, is much greater at the tip. So that rotational velocity component, omega r, is much greater near the tip. And what we see if we compare these diagrams is that the flow angle, phi, is much greater near the root than the tip. Now, it's worth pointing out and noting here that that flow angle is not the same as the angle of attack. The two are very slightly different, and we're going to show this in the next few slides. Now that flow angle is the angle that the flow makes relative to the rotor plane and not to the aerofoil chord line. So we're going to go into that in a bit more detail, but for the moment it's worth just remembering that that flow angle phi is different to the angle of attack. So I've given here another blade element diagram, this time to show you that actually the flow angle phi is actually the sum of the angle of attack, alpha, and the pitch angle of that local aerofoil section relative to the rotor plane. So what you can see is that actually if the aerofoil section is aligned parallel with the rotor plane, so there's no twist, then beta is 0, and the angle of attack is the same as the flow angle. But what beta allows us to do is if we pitch that aerofoil section into the wind, so from our diagram we rotate that aerofoil nose down, we increase the pitch angle beta, and therefore because the flow angle is fixed, then we reduce our angle of attack. So what this diagram is showing us is that actually that flow angle phi is fixed by the wind speed and the rotational velocity component, and we want to not encounter stall. So we need to make sure that the angle of attack alpha doesn't get too large. And the way we do that is by twisting the aerofoil sections through that angle beta as we go along the blade. So now it's worth thinking back to our entire blade. Remember there we just took a single section, a single slice through the blade. And remember that those aerofoil sections near the root have a large flow angle phi because the rotational velocity is small, and therefore we have to have a large twist angle for those aerofoil sections. So beta has to be large in order to limit that angle of attack alpha. Whereas at the tip, the rotational velocity component is large, so the flow angle phi is small, so we don't have to twist the aerofoil sections. And what this results in is that when we look top down on an aerofoil, on a blade, what we see is that those aerofoil sections near the root, the very big ones, are twisted and pitched into the wind quite a lot, whereas the small sections near the tip are not twisted very much at all. So this is the main reason why wind turbine blades are twisted as we move along them. It's because the sections near the root are rotating relatively slowly, and in order to prevent stall, we twist those sections into the wind to limit our angle of attack. Now, what happens when the wind speed changes? So in a typical environment that you might install a wind turbine in, that free stream wind velocity is going to be varying continuously, varies all the time. And so what happens to the blade under these conditions? Well, I've got two diagrams for you here. On the left, we've got a diagram where the free stream wind speed is very small, and on the right, I've got a diagram for you when the free stream wind speed is very large. And what we see is that as that free stream wind speed picks up, so as the wind accelerates, then the flow angle phi increases. And of course, the twist angle, beta, of those local aerofoil sections remains constant. It's how we've designed it. And so actually the angle of attack increases as the wind speed picks up. And this could be potentially bad for us, because that might mean that as the wind speed picks up, then some of our aerofoil sections may start to stall on our wind turbine rotor. And this is something we want to avoid. And so what we do is we need a control system in order to limit that angle of attack and prevent the sections along the blade from stalling. So what control mechanisms could we use to control our blade? Turns out there are two options which we can use. We can either change the rotational speed of the entire rotor. So as the wind speed picks up, what we do is we spin the blades faster. And what that means is, if we look at our diagram on the left, as that wind speed, as that vertical velocity component increases, then we spin the entire blade faster, which increases that horizontal component of the triangle, and this in turn reduces our angle of attack alpha, so we avoid stall on the blade. Now, the other option is that rather than spinning the rotor faster, which we may not always be able to do, what we do is we pitch the entire blade. So we take that entire blade and we have a motor at the root, and what we do is we pitch the entire blade. And what that will do is that will increase beta. As you can see from the diagram on the right, is that we've increased beta along the entire blade. So even though our flow angle has increased, we've increased beta along the entire blade by pitching the blade, and what that means is that our angle of attack alpha is reduced, and so we can avoid stalling our wind turbine rotor using that method. Now, it turns out that the control systems in a wind turbine rotor to pitch the blade and to vary the speed of the rotor are very complex, so we're not going to go into too much detail on them here. However, I do hope from the preceding slides you can get an appreciation for how these control systems function and what their aim is. Their aim is to reduce that angle of attack so that we're not stalling the rotor along the blade. And it's worth also noting that both of these control mechanisms are actually used in modern wind turbines, but they're used at different periods during the operation of the rotor. So speed control is typically used before we reach rated power, so this is at relatively low wind speeds. As the wind speed picks up, we spin the rotor a bit faster. Whereas at high wind speeds, when we've gone beyond rated power, we tend to pitch the blades. But I'm not going to go into too much more detail on these control strategies here. And really, if you want to know more detail, it's worth diving into the literature and looking at these control strategies in a bit more detail. For now, the main reference I can provide for you for further reading is the Wind Energy Handbook. This is a really essential textbook for all those interested in wind turbines, wind turbine control and wind turbine aerodynamics. And as always, I'll provide links for that reference and for others in the comments section below this video. And I look forward to hearing your feedback. Do you have any questions? Was there anything that I could improve in this video? And what would you like to see in future videos? Until next time, I look forward to hearing from you.